I'm going to cheat, not really cheat, but I'm going to do a quick way of finding it. Oh, it looks like I tried to find it the other day. There we go. Okay, so what we have to look for is the constellation of the flying horse in Greek mythology, and its name's Pegasus. And you'll notice it right here, the flying horse, and it's kind of flying upside down. I kind of don't know why. I have a feeling it's because they thought this looked like a head, and these are feet, and there's a wing right there. So Pegasus is kind of flying upside down, but hey, there's no right side up or upside down in space, so I guess it doesn't really matter.
They had a vivid imagination.
They did. You know what? Some constellations look very much like what they're supposed to. But some constellations, really, you have no idea why they would have thought they would look something like that. So I would say Orion, who is right there, kind of does look like a hunter. I mean, you could think of, there's a shoulder, there's another shoulder, there's a foot, another foot, a belt, very obviously, a sword hanging down. Maybe he's holding something, and there's his head, it's really small. But anyway, other things, it would be very hard to tell. That you kind of wonder why they would think it looked like what they said. But anyway, Pegasus, what you look for is something called the Great Square. And here we're looking kind of southwest. Look up from west-southwest, and you should see it actually looks more like a rectangle. So I'm going to take the artwork away, and there's the rectangle right here. This is called the Great Square of Pegasus, right there. And I'll put in some lines just to show you. There it is. Okay, so to find the Andromeda Galaxy, we can use a technique called star hopping, because, you know, even in a dark sky outside the city, it's not that easy to see, but you can see it with your naked eye if you have a really dark sky. What you do, you go to this upper left star in the square. So there's the square right there. You go to the upper left star, and you go over in this direction, over 2 stars. So there's 1, there's 2. Okay? And then you take a right turn. You go 2 stars to the right, 1, 2, and you get to this star right there. Now, if you take a close look, I'm going to zoom in on a little bit. You'll notice that right near that star, there's a hazy patch. And you can see it right there. I'm going to zoom in on that. And that is the Andromeda Galaxy. So I'm going to zoom in on it. Here we go. And in a telescope, if you took a long exposure photograph of it, you'll get a nice, and stack the images and did some image processing, you'll get a nice view kind of like this. Andromeda Galaxy is very similar to the Milky Way. We used to think it was a lot bigger, at least somewhat bigger in size. We think now the Milky Way is a little bit bigger than Andromeda. That's the most recent estimation. Anyway, this is what a galaxy kind of normally looks like. You have a lot of stars, and they just look like a globe because they're so far away, obviously. And you notice some darker areas right there. Those are dust lanes, and there's a lot of gas in the galaxy itself too. So a lot of nebulae in the galaxy itself also. So we call this the center or the core of the galaxy. And surrounding the core, we have what we call spiral arms. So it's actually a spiral. If you looked at it kind of, we're looking at it a bit more edge on. If you could look at a galaxy kind of front on, you'd see it was more kind of a spiral shape. Now, if this were the Milky Way, just to give you an idea, I believe we talked about distances last time, didn't we? We talked about light years, right? Does everybody know what a light year is?
Can't explain it.
Okay, so let's think of it this way. How long did it take? Back in about 51 years ago now, the first moon landing took place, Apollo 11. How long did it take the astronauts to get from the Earth to the moon in their spacecraft, in their command module?
2 days?
That's close. It was actually about 3 days. So that's pretty much what we can do right now, about 3 days. You have to make sure that partway through your trip that you slow down. Otherwise, you might keep accelerating. You'll miss your target. So partway through, you have to fire your retro rockets so you slow down, actually. In space, all you have to do is accelerate to the speed you want to go, fire your rocket engines, and then turn them off, and what you do is coast. If you kept accelerating, if you kept your engines on, you'd keep accelerating. So if you want to reach the moon, you wouldn't want to keep accelerating and accelerating and accelerating, because you'll just go faster and faster. But there'd be a limit to what your engines could do. And it's nothing like the speed of light, nothing anywhere near it. So if I clicked on one of these stars right here, okay, so let's get back to this. So traveling at the speed of light, how long would it take you to get to the moon, do you think?
Five minutes? 5 minutes.
Actually less.
Oh.
1.5 seconds, right?
Yep, it's a little over a second.
Wow.
So that gives you an idea. I mean, I can quote, I can say it's 186,000 miles per second, which it is, about 300,000 kilometers per second. But that doesn't mean a whole lot when you think about it, though. When you start quoting big numbers like that, people tend to go, well, that's really cool, but what does that really mean? But if you figure you can get to the moon in over a second, traveling at the speed of light, you get an idea of how fast that really is. So how far away would the sun be? How long would it take you to get to the sun at the speed of light?
Because the windows are signal pan.
Is the sun closer than the moon?
Oh no,
it's much further away. Oh, don't know. Maybe 5 minutes now.
Actually, that's not bad. It's about 8.
Oh.
So traveling at the speed of light, it would take about 8 minutes to get to the sun if you wanted to go there. But conversely, it takes sunlight 8 minutes to get here. So when you look at the sun, you go outside and look at the sun like right now, I can see that it's sunny outside, it's filtering through the windows. You're seeing the sun as it was 8 minutes ago, because it took light. The light that left it 8 minutes ago is getting here now, and we see the sun as it was. Okay? So it becomes really interesting when you talk about larger and larger distances. So let's click on a star here. I'll click on this one, and we'll see how far away it is. So keep in mind the sun is 8 light minutes away from the Earth. Okay, this star, and it's given 32 Andromedae, so it's not a big star at all. It's not an important star. So you can look at right here, it says distance 331 and almost a half light years. So it took light 331 years traveling at light speed to get here from there. So you're actually seeing that star as it was 331.5 light years in the past. So the further out you go, you're seeing the object as more into the past.
What about in the past, that same star, would it have still been 300 and so, like 100 years ago? Would it have been still that far away?
yeah, chances are the time scale of the universe is such a long time. I mean, who knows whether it was even infinite? But the time scale, the size of the universe is just so huge that chances are thousands of years ago, many thousands of years ago, millions of years ago, the sky would basically, look pretty much the same as it does now. Some changes, especially in the nearby stars and their positions, possibly. So this star, we'll just talk about what it is now. It's about 331.5 light years away. So all of these stars here, they're different distances, but they're in our galaxy. So let's look at New Andromedae. It's actually given a Greek letter. It's a little more important than if you give it a number, I guess. So let's look at this one. How far is this one? 617.7 light years. So this is further away than this one. That's further away. Let's look at this one here, maybe. That one, 658.9 light years. So you can click on any of these stars and you can see how long it took light to travel from there to here in this program. Now, here's the thing. All of these stars there are in our galaxy. So you're looking through those stars out towards another galaxy here. There's nothing really, no stars between galaxies. Sometimes galaxies can eject stars that have a big velocity, but generally there's no stars between galaxies. It's just a big void, basically. Obviously, there are some molecules in that space, but you won't have stars themselves.
Excuse me, Alan, can I ask a mini question? Is if it's okay. So I had heard recently they were saying that between the galaxies was actually dark matter, but there's still a lot of speculation of what that is or isn't. But they said there was.
We don't know. We still don't know what it is.
Yeah.
To tell you the truth, dark matter has been thought up because, and we'll talk a little bit about this. The universe we know is expanding. All of the stars, all of the galaxies are getting further and further apart from each other. And so the universe is expanding. That's why we thought that it must have started at some point. So we call that point the Big Bang. But we know the universe is expanding. We can actually measure the expansion. And I'll maybe get a little bit into that, how we can do that. But, sorry, what was your question again?
Basically, the space between galaxies is actually filled with dark matter.
Yes. So anyway, dark matter was put into the equation because we noticed that this expansion of space is actually accelerating, which kind of shouldn't happen, right? If there was like a big explosion or whatever, matter should like spew outwards from and keep going and going, but perhaps slow down, perhaps go at the same speed, but it shouldn't really be accelerating. Something must be gravitationally affecting the expansion of the universe. Therefore, we thought there's something maybe we can't see.
So the dark matter is moving.
The dark matter,
the dark matter's expanding.
well, the dark matter is there and it's gravitationally affecting the expansion of the universe. Thing is, we don't know what dark matter is. Some people are actually even contesting that it really exists. Maybe we just haven't, thought up or haven't calculated things properly. But right now, physicists are kind of standing by the dark matter hypothesis. And dark energy is actually it's kind of a repulsive force in the universe, kind of pushing everything apart. What is dark energy exactly? We're not exactly sure. But it helps to explain this accelerated expansion. So it kind of remains a mystery right now. But anyway, getting back to the Andromeda Galaxy, if this were the Milky Way, from end to end, it would be about 100,000 light years. So from this end to that end of the Milky Way would be about 100,000 light years across. And that shows you how big, let's say, our galaxy would be. We're thinking now that the Andromeda Galaxy is a bit smaller than our galaxy. So you'll notice also that Andromeda has a few satellite galaxies. There's one right here, one right here. And we do too. They're called the Magellanic Clouds, and you can only see them in the southern hemisphere. Like if you went down to Chile, you have to go way far south in the Earth to see them in the sky. And they're actually our companion galaxies as well. So the Andromeda House has a few companions. We have a few companions. How many stars in a galaxy? Well, in our galaxy, the Milky Way, we estimate, and there's a big plus or minus here. The lowest estimate would be about 100 billion. The highest estimate would be about 400 billion. So it's probably somewhere between those two. And if you want something really mind-boggling, how many stars would be in the universe? I mean, it has been calculated, the observable universe, it has been calculated with how many galaxies there are, how many stars could be in a galaxy, that sort of thing. But, I mean, I could quote you a number, I'd have to look it up. But maybe better than that, think of this, that there are about the same number of stars in the universe as there are grains of sand on every beach on the Earth. Now, if you can get your heads around that, that's pretty incredible, you know? So another amazing thing is that most stars, at least we can talk about our own galaxy, most stars we feel have planets. So what does this mean? It means that there are more planets than stars in the universe. And you know what, to me, that definitely would make the possibility of finding life a lot more possible. Because as far as we know, life needs planets to start up on. So not all planets will have life, obviously. Maybe more planets don't have life than do, but you need planets for life. So it's great to know that most stars have planetary systems as far as we know. So to say that, we've taken, we found, I believe, I'd have to look up how many we found. I think it's a few thousand planetary systems now around other stars by indirect methods. And so we kind of extrapolate that number. I'd have to look up exactly how many we found so far, but we just extrapolate it to the size of our galaxy. We can't see all of our galaxy. So for example, if this were the Milky Way, we would be about 2/3 of the way out. We'd be maybe about there. Okay, we'd be in one of the spiral arms, about 2/3 of the way out from the center. The other interesting thing about galaxies, we realize that probably most galaxies have what we call supermassive black holes in the middle. And we know our galaxy does, so we think that other galaxies most likely do also. And so we'll talk a little bit about black holes in a sec. The other neat thing about, remember I said the universe was expanding? So all galaxies, if you look at them, you'll see galaxies move away from us. But if you were, let's say, in the Andromeda galaxy, you'd see all galaxies move away from it. And if you were at another galaxy, you'd see all galaxies move away from it. So it's kind of a generalized expansion of the universe that way. It's almost like if you had, I don't know, if you were making raisin bread and raisins were galaxies, and then you cook the bread and everything expands and the raisins all get further apart, but they kind of stay where they are, but they get further apart because the whole universe is expanding. That's kind of how it goes. And one neat thing, though, is that this Andromeda galaxy, we've measured it, and it's actually coming towards us. The relative motion of the Andromeda galaxy, it's on a collision course with ours. And when is it going to arrive here and collide with ours? In about 5 billion years, we figure.
Excuse me, Alex.
Yeah.
I'm me who asked all the questions. Sorry about that. So
Okay.
if everything's moving apart, how is it colliding?
Yeah, I was thinking that too.
Okay, yeah. Well, generally space is expanding, and it is, but the Andromeda galaxy is one that has a proper motion of its own. And if you take a look at individual galaxies, there's a generalized expansion to the whole universe, but this galaxy, we're very close to it. So in the expansion, it has, it's all I can say is it seems to have a proper motion that is going to bring it closer to us. I know it kind of sounds weird when I said the whole universe is expanding, but when you take a look at a smaller area of space, you get some things happening that you don't exactly expect. So that's we have measured its kind of relative motion, and its relative motion is towards us. We're moving out with the whole universe expansion, so is it, but it also has just in this region of space, it just has a proper motion towards us. And for more explanation, I'd have to look it up too, I guess. But it's going to arrive here in about 5 billion more years. And here's the thing, what's going to happen to us when that happens? Well, you can go onto the internet and look at some computer simulations of what might happen. There won't be too many star-to-star collisions, believe it or not. It almost looks like one galaxy will pass through the other one, and with not with hardly any stellar collisions. You might get some gas colliding, maybe some heating up of the gas that's in the galaxy, but you won't get a lot of stars colliding. So the Earth might actually survive that. But then they're going to move apart, and then because they're so close together, they're going to move back together again and do that a few times, and then merge and form what we call an elliptical galaxy, which is kind of a big galaxy full of old stars. And so that's kind of the fate of the Milky Way. But at the same time, that's not the only thing that's going to happen to us. That's in 5 billion more years. In about 4.5 billion more years, we have something even more dire that's going to happen for the Earth. So anyway, I'm going to zoom out. And what you see here, and you can see some of it here. Can everybody see kind of a hazy, smoky area? Mm-hmm. Okay, we call that the Milky Way. And you'll notice it goes right through the constellation of Cygnus. I think I pointed Cygnus out last time. Cygnus is right there. It's a swan. There we go. It's kind of flying south. Anyway, so these are the spiral arms of our galaxy. So what we're looking at here is we're looking right into the spiral arms. And you see all of this very far away, stars, dust, and gas. And there we're looking right into the plane of the spiral arms of our galaxy. And you won't be able to see this from Toronto. You really have to go out into a really dark sky. Into cottage country, you can still see the Milky Way. And so if anybody has the opportunity to do that, you'll find it's quite beautiful. Okay, so anyway, what I'm going to try to do, let's take a look at some stars. So let's go to Orion. Let's go to Orion, my favorite, right here. And it's very recognizable. Right near Orion, by the way, you have this star right there. It's the brightest star we can see in the sky from Earth. It's called Sirius. And it's in the constellation of the big dog, Canis Major. So he's one of Orion's hunting dogs. The other one is a small dog, Canis Minor, and that's him right there. So Sirius, I'm going to click on Sirius, and let's see how far away it is. It's a very bright star. It's the brightest star we can see from Earth, other than the sun. I'm sure everybody realizes the sun's a star too, right? And it's so bright because it's close. So let's see how far away this is. Distance, 8.6 light years only. So it's close. So it's bright, probably because it's close. Okay? So let's just look at a few of these other ones. Betelgeuse. I'll click on it. We have 400, almost 500 light years away. So it's a lot further away, but it's still pretty bright. Rigel, click on it. 862 light years away. And it's also fairly bright. So they must be really powerful stars to shine as bright as they do and be that far away. So does everybody kind of follow so far?
So the stars, we see the light of the star, but that star could be bigger than the sun, only millions and trillions of miles further away.
Some of them, yes, but some of them are definitely bigger than the sun, definitely. And we'll take a look at that coming up right now, actually.
But nobody's ever been able to put a telescope that close to them.
No, like if you put a telescope on any of these stars, this is how you can, this is a really good way of telling the difference between a planet and a star if you're not sure. If you put a telescope on a star and you magnify it, all you'll see is a point of light. You won't see a disk. You'll see a point of light. It's just so far away. If you put a telescope on a planet and magnify it, you'll actually see a disk because it's close. So anyway, let's just to give you an idea, before I go into the different types of stars, let's look at these ones. So this one we said was this is about 500 light years away.
And that's just the tip of that's just the light, not the actual star.
That's how far away the star is. So it took light 500 years to travel from there to here. This one is about 862 light years away, so it's further. This one, 252 light years, so that's closer. This one, 647, so that's still pretty far away. I'll just do these three. This one, 817. This one, 1,976. This one, 916. So as you can see, some of them are radically different distances, but yet we see them as the constellation of Orion. So here's the thing. They're not really close together in space. It's just our perspective. They're not close together in space. Realize space is three-dimensional, right? They look like they should be close together because they're in the same constellation. But really, if you could go way out and look at them from the side, you'd see that they're all different distances. We just see them that way because it's from our perspective. Okay, so what I want to do now is talk to you a little bit. Now we've gone a bit over light years. let's take a look at different types of stars. To find the type of star it is, what you can do is click on this, and here's Betelgeuse, and you go way up to type. This is called a pulsating variable star, a double star. So in fact, this star has more than one star in the system. It's like another star revolving around the other one. And a pulsating variable, different stars actually vary in their light. Not all stars do that, but some stars do. So to get the type of star, we go to something called spectral type. So I'm going to show you what that all means. And now I'm going to try to do some screen sharing and you'll have to tell me if you still see my screen share. Let me just check. Here we go. Let's see now.
Yeah, we can see that.
Can you see that?
The stellar classes and spectra and yeah.
Spectral class types of stars.
Yes.
Perfect. I did it. I'm a newbie at this. Okay, you have to realize I'm a newbie at this this virtual stuff.
This is easy compared to what you're talking about.
Oh yeah, I know. Well, I'm hoping that I share properly. Just let me know if you can't see something. Okay. So anyway, when you look at a star visually and through a telescope, you can really see this. Stars are actually different colors. The colors range from kind of a blue-white over here on the left to kind of a reddish over here on the right. And it almost goes through the spectrum in a way. So we have kind of blue-white, getting more white, fairly white.
We're not seeing that.
No, it's
Okay.
It's not as obvious, right? This one.
No, I mean on your screen. We're only seeing the list.
Oh, you're just seeing the. Oh, I see.
Yeah. We're not seeing what you're talking
Oh, you're not
about.
seeing that. Okay. Okay.
Double click on it.
Well, you figured that you have to go back into stop sharing.
Stop sharing. Okay.
Go back into share screen.
Share screen.
Right, then you have to pick that.
This one?
Yeah, pick it.
What if I pick this one? No?
Well, try it. What do you want people to see?
Well, this one for now.
So they do that. There, can they see that?
Okay, now we can see a rainbow.
Okay, so if I wanted to, I'm going to want to do some of these other ones right after. So we'll stop sharing. Go back. Okay, I'll give it a try, hopefully. Okay, so what we see here, ranging from kind of bluish white all the way to kind of orangish red. And we have the different spectral classes going from blue, blue-white, getting more white, white. Think of it like blue-white hot. If you're welding, like a blue-white hot is a lot harder than red hot, right? Blue-white, a little less blue-white, white, kind of whitish, yellowish white, kind of yellowish, orangish, yellowish orange, getting to kind of more of an orangish red. And we give the names to the different classes of stars. Class O, I don't know why they choose these initials, to tell you the truth, but we have a mnemonic that you can actually use to memorize these spectral classes. We have O, B, A, F, G, K, and M. And it's even in astronomy books. The mnemonic would be, "Oh, be a fine girl, kiss me."
Yeah.
Or you could say, "Oh, be a fine guy, kiss me," right? So whatever. But "Oh, be a fine girl, kiss me" is it's actually in astronomy books for you to memorize that. But you can make up your own mnemonic, right? Okay, so what does this mean? Different stars are different colors. So what actually affects the brightness of stars? There are many things that affect the brightness of stars. One is the color. Like a hot blue-white star will look brighter than a cooler red star because the hot blue-white star is giving off more energy. So it just looks brighter to us. Another thing is distance. So the further away a star is, the dimmer it will look. And you may know from physics, it's an inverse square law. So for example, if I took a star and moved it twice the distance, it goes down to only a quarter, or 1/2 squared, so a quarter of the brightness. So if you took that star and moved it 3 times away, how bright would it appear to be?
Whitish.
Yeah, but how bright? So like if you took a star, and it was a certain brightness, if I moved it to twice the distance, it's only going to look a quarter as bright. So if I took a star and moved it instead of where it is to 3 times its distance, how bright would it look as opposed to what it did?
Less bright.
So the first one was 1/2 squared, which is 1/4, so it's a quarter. So this would be 1/3 squared, so it's only 1/9. Okay, so if I moved a star 3 times further away, it only looks 1/9 as bright. So here's the thing. So distance is a factor. Another thing that's a factor is something called luminosity. It's how much energy the star puts out. And generally, the blue-white stars are more energetic, so they will be brighter. Also, how much material, like dust and gas, is in the way. That affects the brightness of stars. So if there's more material, it actually makes the brightness less. So there's a lot of factors that can affect the brightness of stars that you see.
So in the desert, maybe in the desert, they'd be clearer?
Oh, well, and you know what? If you go out into the desert in a totally dark sky, everything will look clearer and brighter than if you were in like a city, right? But that's everything. I'm talking about individual stars, right? And the difference between individual ones. So here's the thing. How do we know what a star is made of? Does anybody know how we can tell? We can actually tell what's in a star.
You could tell by the light.
By the color.
Yeah, okay, so it does vary with the color. What do we do? And a lot of work was done at the David Dunlap Observatory, the observatory north of Toronto right here. A lot of work was done on this. And what you do, you may remember from physics classes when you took light and you took a prism and you split up the light.
I never had a physics class.
Right, but you split up the light into colors, right? I mean, a light going through a prism splits up into colors,
right.
Rainbow, right? So you can do that for stars. We take, you can use prisms, but we take something called a spectrograph grating, but it does the same thing. So it splits up a star's light into component colors. And I'm going to show you. So try to remember, "Oh, be a fine girl, kiss me," okay? Okay, so I'm going to see if I can do this correctly. There's stop share. Okay, now. What I want to do is get this screen now.
Stop share.
I stopped shared. Now,
Go back. So click on that.
yes?
Yeah, click on that.
Okay.
Go back to your thing. Go back to the Zoom window. Click on share.
Share screen.
Share screen. Then you click on that.
This one.
Yeah. Click on that. There you go.
Okay.
Can people see that?
Can everybody see this? Whoops.
Yeah.
Good.
Okay, what I'd like to do is make it bigger. Oh yeah, I can make it bigger this way. That's
Yeah,
right.
go for that, yeah.
All right, thank you. I may need your help a few times, but that's okay. Okay, so what we have here, there's the spectral classes. So there's Oh Be a Fine Girl, Kiss Me right here. Okay, so these are the hot stars, surface temperature 30,000 degrees Kelvin. And Kelvin is, well, it's a scale of temperature in the universe where you can't get any colder than 0.
Oh, be a fine girl, kiss me.
Okay, so for example, 0 degrees Kelvin is the coldest you could ever get. It's actually minus 273 Celsius. It's the coldest you can ever get in the universe. So about 30,000 degrees Kelvin. Oh, sorry, this is actually surface temperature in Celsius. Sorry about that. I made a mistake here. They've converted it to Celsius, so it's more understandable to everybody. So these stars, the hot ones, when you look at the spectrum, I'll try to zoom further, you'll notice a rainbow, but you'll also notice some lines in there, right? Do you see those lines?
Mm-hmm.
There's one there, one there, one there. And you'll notice that these lines are slightly different depending on and how many there are, what the intensity is, and the positions of them. They're slightly different for the different types of stars. So this is like a blue-white star, less blue-white, white, yellowish, white, yellowish, yellowish or orangish yellow, and then maybe reddish orange, okay? So you'll notice the temperature goes down, and look what happens. These lines are different intensities, maybe more of them sometimes, and by looking at a spectrum, we can tell by the position of these lines what elements are in the star, which is pretty neat. So all you need to do is take a photo of the star, put it in a spectrograph, and look at the lines, and you can determine from reference spectra that you've done in a lab, let's say, what line means what element. So that's how it's done. That may be
elements being like, well, not calcium, but certain gases. Like elements, what kind of elements?
Well, things like hydrogen, helium, lithium, beryllium, you know,
okay,
carbon, nitrogen,
I don't know, yeah.
All of that.
Getting too complicated. It's getting too complicated.
Okay, so I'll make it fairly simple. Hydrogen is the most common element in the universe.
Okay.
Generally, stars take hydrogen atoms and they fuse them together and they make helium by nuclear fusion. That's what our sun's doing. And a lot of heat and a lot of light come out, and we benefit from the heat and the light in that process. Hotter stars burn this hydrogen fuel quicker. The cooler stars burn it much more slowly. Our sun is actually type G. So we're fusing hydrogen to helium. We get heat and light coming out of it. And we benefit from the heat and light, obviously. Now, the sun's been around. The sun's formed out of a nebula that had been there. We've been around for about 4.5 billion years, we figure. So we're about half our life gone. In another 4.5 billion years, though, the sun is going to run out of its hydrogen supply. So what it does then, it starts to take helium atoms and fuse them together, making heavier elements. But to do that, there is a lot of changes. So I'm going to show you a few things that happen, okay? Hopefully this will work. So I'm going to stop sharing this screen. I'm going to go to this one. Okay, so I'll go to this one. Okay, so, yep. So what I want to do is go back to our Zoom screen.
And share it again.
And share the screen. Okay. This one right there.
You can see what you want to share.
And it's this one. Yeah. And go share. Okay, does everybody see this?
Yeah, make it bigger.
Okay.
Oh, you've gone back.
No, I'm going to make it bigger.
Yeah.
There we go. Okay. So if you took, I know this might sound a bit technical, but I want to show you, I'm going to go back to Stellarium and show you what this all means, okay? If you take a lot of stars that we can see and make a graph. So we have temperature along the bottom, and going up here we have size, we have luminosity, which is energy output. And if we made a graph like this, most stars that we see lie along this line. It's kind of a diagonal line in this graph. We call it the main sequence. All it means is blue, whitish stars tend to be larger than the reddish, cooler stars. We also get some stars that are kind of strange. We get some giant ones. We get some really big ones called supergiant ones. And we get a special class of stars down here called white dwarfs. You may have heard of supergiants, giants, white dwarfs, maybe. I don't know. Our sun, we call it a G, type G, yellow dwarf. So it would be about here in this graph. So now, all of this, I'm going to show you kind of what's going to happen to our sun. You'll notice these giants and these supergiants up here. Those are later stages of a star's life. A star normally spends its time in this, what we call a main sequence area. These other areas are later stages of a star's life. So I'm going to show you what happens to the sun, and then I'm going to show you what happens to other stars that might be bigger than us. Uh-oh, what did I do? Maybe I can still do it, okay? There we go. I think I'm doing it okay. I think I'm okay. And I go back to here, and I go share, and that's it. And now I can go.
Yay. Great.
Whoops. There we go. Okay. What you see here is what happens to stars in their lifetime. Now it's going to be a bit fuzzy. It was a small picture, so when I make it bigger, it's a little harder. So I knew what to see, but anyway, all stars are formed out of gas and dust clouds. So we assume that our sun and some other stars in the neighborhood would probably formed out of the same gas and dust cloud, called a nebula. So a star that's an average star, like what would be on the main sequence, like that diagonal thing I showed you on, that was called an HR diagram. This is our sun right now, okay, right here. It says average star, okay? Now in about 4.5 billion years, our hydrogen supply is going to be used up, and we're going to start fusing helium, but changes happen to the star when that happens? Our sun is going to turn into what we call a red giant star. It's going to swell up, look much more red, but it's going to be a lot closer to us. The edge of the star is almost going to reach Earth. We have to be gone when that happens.
No.
Seriously, we're going to be fried. I mean, Venus will be inside the star, okay? We're going to be fried. Oceans will boil away, temperatures will skyrocket. Life just wouldn't be able to exist under those conditions. Sometime later, I'd have to look up how much later. It stays in the red giant stage for several million years, but I'd have to look that up. So it's about 4.5 billion more years to go from where we are now to the red giant stage. And then I'd have to look up how many more time. I believe it's millions of years. I'd have to look it up though. Instabilities of the star, it's going to kind of blow off its outer layers, and some of this material will go back to form dust and gas clouds and leave this core, which is what we call a white dwarf. It's kind of the core of our sun, and it's going to stay around for quite some time, but then it's going to cool off, and then that's it. So that's going to happen to our sun. I'm sorry. I don't have better news. But here's the thing. The Andromeda Galaxy, like we said, is going to collide with us in about 5 billion years. Before that, in about 4.5 billion more years, this is going to happen. So we have to be out of here. You know, this is what's going to really destroy us, not the Andromeda Galaxy colliding with us. Now, here's the thing. If our star were more massive, so let's say a much bigger star, let's say about 10 times to the mass of our sun or more, instead of, it'll stay on the main sequence for a bit. It'll burn hydrogen to helium. But then, instead of just a red giant, it's going to form a huge thing called a red supergiant. And we see some of these stars in the sky. That star in Orion, Betelgeuse, is actually one of them, a red supergiant. Now, the size of this star, if you took it, put it in the place of the sun, we'd be inside the star right now. It would be almost up to the orbit of Mars, just the star. What will happen to it, chances are, is a huge explosion. Instead of just the outer layers blowing off into space, the whole thing blows up in a huge explosion called a supernova. And the star becomes so bright, you can see supernovas even in other galaxies. Now, what will happen with that is two possibilities. The core of the star could collapse, so it's way too big just to form a white dwarf. The core of the star could collapse into something we call a neutron star. So what happens there, all of the you may remember from chemistry, protons, neutrons, electrons, right? All of the protons and neutrons smack together to form neutrons. Protons and electrons can form neutrons and are just crushed. And we have a star that actually is very, very massive in a small space, and it only lets light out. It has a huge gravity. It only lets light out in certain directions, and it rapidly spins. And many of these stars are called pulsars because when we look at them, they look like they're flashing on and off. Isn't that weird? But if it can actually, sometimes if it's very massive, the core can collapse and keep collapsing, and we form what we call a black hole. So that's what a black hole is. It's kind of the end product of a stellar evolution of a very massive star. Okay, so any questions about the stellar evolution thing? I can't exactly tell you some of the time frame for a few of these stages. I'd have to look it up.
But maybe something else could happen in the universe to stop that. I mean, this is speculation. I mean, you're saying millions of years from now.
Here's the thing. We, whoops. Let me see here.
So Mike, while you're just in transition, I just want to welcome Nina's on board now. She's our program coordinator for this wonderful afternoon program. So welcome. Remember, everyone remembers Nina from Little Rainbow Fish. Welcome, Nina. All right.
Hi. Okay, so just one more thing I want to show you, then we'll go back to Stellarium, and I want to show you a few of these different types of stars that we've talked about. They're there. Okay, so now let me see that I'm doing it okay. Share screen. Does everybody see this?
Yeah.
Oh, good. Okay, so I'm just gonna. Everybody see that? It's from chemistry?
Yeah.
Oh, good. Okay, perfect. Okay, so this is your periodic table. You may notice from chemistry class. It's back to haunt you. In any case, you may wonder where we get all our elements from. And it's from stellar evolution. So if you look at this, some elements were made during the Big Bang, hydrogen and helium. That's why they're coded blue. We have dying low mass stars, kind of like what the sun would do when they start burning, fusing helium into other things. Some of these things are in green: lithium, carbon, nitrogen. And some of these elements down here, they're in green. Exploding massive stars, like supernovas, they would form, they are mainly responsible for forming the elements that are shown in yellow. Okay? Now, where do we get some of these other things? Something called cosmic ray fission caused by cosmic rays. There are a few, beryllium's one. Merging neutron stars. If a neutron star collides with another one, we can actually get some of these heavier elements formed. And these gray ones at the end, they're made by humans in a lab. And they only last, they're very radioactive. They only last for a very short time. So stars, the evolution of stars forms the elements we have in our universe. That's where we get our elements from. Okay, now what I'm going to do is try to go back to Stellarium here. And let's see how to do that. Okay, so what I want to do is just go back to Stellarium and take this window out.
So go back to your, should be somewhere in Google, go to Google Chrome, I think it's this. No, it's not there. And go back to your desktop. It was on your desktop.
Here?
Oh, there it is. There's Stellarium in the back. Oh, I can see it. Okay. See, it's still operating. So go back to.
It's in the back.
Yeah, so let's see what happens.
I'll just step out of the way here.
Yeah, and where's Stellarium? Right there. I just saw it. Well, if I
there it is.
If I do that though, but then we've got to figure out how to get back to the. Yeah. Hold on a sec. There's a way. There's the menus. I go.
Okay, that's getting out of stellarium.
Yeah, but I want to go back into it and share. You know, we should probably just close some of these windows.
Yeah, I think so.
Got a lot going on there. Okay. Can we close that? I don't even know how to close that. I don't know how to do that. Okay.
Could we close all of them? Just could we close that whole screen?
Let's see what happens. Oh, let's see what happens here. Hold on. Go back in. So I close that. Okay. And then am I closing that too? Good. Okay, good. Good.
Okay, we're just closing all of those, so that's good.
Okay, but okay.
Now we want to get stellarium back.
Stellarium back. Yes, okay. And then we'll go there. It's opening up. Share screen. Where did it go? It did something. Was there a second ago? Oh,
there it is.
But then hold on, you gotta figure out where it is.
It's in the background right now.
You gotta be able to see it though when you go like this. Oh, there it is.
There it is. Perfect.
Okay, we've got stellarium. Yes, okay.
All right. Okay. Thanks a lot. Can everybody see stellarium?
Yeah.
Okay, so I'm just going to go back at night. Okay, back to Orion. Okay, so let's check out what type of stars these are. Betelgeuse. If you look here, spectral type M. Okay, so it actually is 2 stars there. Spectral type M.
The ready one.
Yeah, exactly. So it's a big, and you also have Roman numerals. So a Roman numeral 1 is a supergiant. Roman numeral 2 is a subgiant. Roman numeral 3 is a giant. Roman numeral 4 is a subgiant. And a Roman numeral 5 is a dwarf. So if you take a look at here, just so you know, spectral type M1. So it's what it is. It's a red Roman numeral 1 supergiant. It's a red supergiant. This star could actually go supernova, and it's a very likely candidate to go supernova. We don't know when it's going to happen. It might have already happened, and we won't know for 500 years because it's 500 light years away. When it does go supernova, though, we're in no danger. We're far enough away, but it'll certainly be a light show. When it goes supernova, we should be able to see the star in the daytime, which is pretty cool.
We won't be here 500 years.
No. But I mean, let's say it happened tomorrow.
Yeah, well.
I mean, you know what? It's worth checking Betelgeuse out. Look at Orion, check his upper left shoulder. It's kind of worth checking the star out just visually, just to see it hasn't done anything yet. But if all of a sudden you notice something extremely bright where the star was, you know what's happened. Okay, so let's look at Rigel, another star. Spectral type, B. Now, B8 just means it's almost OBA, so almost to A. It goes from 0, 1 to 9, B, 1 to 9, and that sort of thing. So we have, it's basically type B1. So it's kind of a white, bluish, a little bit of blue, white, another supergiant star. It's big. Okay. This star right here, spectral type B, but then Roman numeral 5. What did that mean?
Giant something. Dwarf. No, dwarf.
It's a dwarf. It's just a regular sized, average, smallish star, but it's type B, so it's kind of bluish, whitish. Hotter than the sun. This one. It's a B1, again, like a white, bluish supergiant. Okay, so some of those stars are very big, actually. This one here, Aldebaran and Taurus the Bull. Check this out. K3. So this is your red giant. This is what the sun's going to be like in about 4.5 billion more years. So here's the thing. We see stars in these various stages of evolution, and we can tell what's happened with other stars, what's going to happen to the sun. That's kind of how we know. Just to show you, way back in 1000, forget the exact date. I always think of 1066, the Battle of Hastings in England. But there was Chinese astronomers that actually, around that time, actually noticed a new star in the sky, very bright. And we know exactly where that was. So I'm just going to show you where it is. It's actually in Taurus the Bull. I'm just going to put this in. It's right here. And what's left over of it is right there. This is a star that actually went supernova in 1000, near 1000 AD. I mean, I have to look up the exact date, but I always think of the Battle of Hastings, 1066. But anyway, this is what's left behind. And it's called a planetary, it's a supernova remnant. It's like left behind after the huge supernova explosion. And in the middle is the star which did it, the culprit, the leftover culprit star. It actually is a neutron star pulsar. We can actually see this star apparently flash on and off. Believe it or not, it's about 30 times a second because it's rotating so quickly. And it's only letting light out in certain directions because of its huge gravitational field. This is called the Crab Nebula. Okay, so here is the supernova remnant right there. So what's happened? Elements have been formed, those heavier elements, right? Like I showed you on the periodic table, and they're going back into the universe. New stars will form out of that gas cloud and incorporate those heavier elements. So we get a whole recycling of elements, making new elements, replenishing elements in our universe, which is pretty cool, eh? Anyway, now something else I kind of wanted to talk about is what happens. There's a consequence of going at the speed of light. I don't know what you'd like me to talk about. I think we have about maybe half an hour left. Did you want me to talk about, remember there was that conjunction that happened back in, on the 21st?
Saturn and Jupiter, that'd be very interesting.
Okay, I could talk a bit about that. And then I could talk about consequences of going towards the speed of light. We can't go anywhere near the speed of light right now. We don't have the technology.
Right.
And in fact, the speed of light is kind of a speed limit to the universe, shall we say, according to Einstein's theory of relativity. So let's take a look at the conjunction business. So I'm going to go back. You can actually go back in time. And I'm going to do that here. I'm going to go back in time to the 21st. So Okay, so I'll go to the 17th, and then we're going to go and find Jupiter and Saturn, because they're the culprits. There's the moon. There they are. Okay. Okay, I'm going to go actually back a little further. Okay. So check this out. This is what the sky looked like at about December 10th. We had, you may remember this, you could look over in this southwest direction and you could actually see two fairly bright objects, one much more bright than the other one, actually, Jupiter and Saturn. And they were fairly close together in the sky. Does everybody remember that?
Well, I remember them talking about it, but we couldn't see it.
I know it was cloudy. Unfortunately, I couldn't see. I went out around the 10th, like here, and I could see them in the sky, but they weren't right near each other yet. But anyway, what I'm going to do is I'm going to focus on Jupiter, and I'm going to take the atmosphere away so we don't get, that's without any atmosphere at all. So we don't get any.
Can you see that?
Can everybody see this?
That's a spiral arm. Yeah.
Okay, so I'm just going to zoom in on them. Okay, there we go. Okay, so I'm going to make the time go by, and it's going to cycle through several days. Okay, so you got to remember, Jupiter is closer to the sun than us. Jupiter is closer to the sun than Saturn. We are much closer to the sun. We take a year to go around the sun. Jupiter takes about 11 point something years. Saturn takes about 29 point something years to go once around the sun. So Jupiter is going to move, from our perspective, quicker than Saturn against the background stars. Okay, so I'm going to increase the speed here of the days going by, and here we go. So we're starting on the 10th. Here we go. I'm going to increase the time. You may see things flitting around. Those are satellites. Here we go. I'll make it go even faster. Oh, geez, just a sec. I got to take the ground out too.
There you go. Get that ground gone. Yeah.
There we go.
Oh, wow.
Got to take the ground out, and I'll put it in telescope view. Okay. Hold on. I'm just trying to get it so you can see it without anything being in the way, and they won't disappear below the horizon. Okay. So here goes. We're now at about the 12th of December. Here we go. Look at this. Jupiter approaching Saturn, there goes the moon, approaching Saturn, really close together. And that is on the 22nd, as you can see down here.
Wow.
And it's going to pass by. Now Jupiter is increasing its distance from Saturn. And here we are about now. This is like January 4th. So as you can see, Jupiter went in almost in front of Saturn. Not quite. It was a little bit away. If you put a telescope on, then they would have been not right on top of each other. But in the sky, they would have looked, you know, brighter than normal when they were close together. It's called a conjunction. And unfortunately, we didn't see it from here because it was cloudy. And no matter what we do, we can't see through clouds. So I want to take you back a long time ago. The neat thing about this program, you could go wherever on the earth, really. So I'm going to go to Israel. Actually, I'll go to Jerusalem because you know what? I think Jerusalem's in the database. You can always put longitude and latitude in of a town, let's say, if you looked it up. I don't think anything else is in there, but I'll just put Jerusalem. Where are we? How would we do this? Oh, here, I'll do this. I'll go to Israel. I've done this a few times, but goes. Okay, now we're in Israel. Oh, now I can do it. Okay, I don't think there's Bethlehem. Nope.
Bethlehem is very close to Jerusalem, by the way.
Yeah, it is.
Yeah.
Well, maybe I can put it here. Okay, anyway, we're probably pretty close because it's right in the Middle East, right? Just wondering why I'm not usually. Yeah, I'll just. Oh, well, I'll just make sure here we go. Okay. So I'm going to put the ground back and just see where it would be. Whoops. And take the ground out, put the atmosphere back maybe. Okay. This will work. Okay, that's just underground. Oh, okay, I got it. There we go. Okay, so, you know, I forgot to do date and time. So we're no longer 2021. I'm going to put it to, just to show you, I'm going to put it to 6, what would have been equivalent to 6 BC. There we go.
1,000 something.
Okay, so we got 6 BC and January 4th. Okay, so let's find now. So this should be, I'll just check that we're still in Israel. This is something I haven't really done a whole lot. So location. Yes, we are. We're close enough. Okay. So this program actually calculates position and date and time and everything. And you can go back, I believe, back about 9,000, almost 10,000 years in the past to 10,000 years in the future, which is really cool. So let's check out, let's find where Jupiter and Saturn would be. So I'm just going to go there and I want to show you something. Ah, okay, so it's below the horizon, western horizon. So I'm going to get up time. There's Saturn, the moon, there's Jupiter. Okay, now this is January. Okay, so you'll notice that there's Saturn, Jupiter, the moon. They're not really that close together. But I'm going to increase the time, and let's see if they get close together at some point. Kind of like what happened this year. So what I'm going to do, I'm going to focus on Jupiter, and I'm going to zoom in on it, and I'm going to take the ground away, and I'm going to take the atmosphere away. There we go. Okay, now hopefully this works. I'm going to make the time go forwards until Saturn and Jupiter are really close together. And we'll check what date. Now that will be another conjunction between Saturn and Jupiter in the year 6 BC, and we'll see what time of year it is. So here goes. I want to make sure I'm still on this. Otherwise, it's going to flip way away from the screen for me. Here we go. Okay, so I'm just going to let the time go by. Okay, there goes the moon. I'm going to make it go real. I'm going to have to make this go really fast. Aha, look what's happening. Look what's happening. Look what's happening. Okay, I'm going to back it up just a bit. Okay, what we have here is the moon, Saturn and Jupiter in a pretty close conjunction, and the moon right with them. And let's see what time of year it is. It shows May 23rd, but I'm going to go a little bit more forward and see if this can even go further. I'm going to zoom in a little bit just to see if we can get even closer. Like the moon will be there. See if we can get closer. The moon will come around again.
Moving away.
Okay, sorry about that. Here we go. Okay, now they're moving apart again. I don't want that, so I'm going to move back. I like that with the moon there. Check that out. Okay.